Welcome to lecture 19. We are going to continue the discussion on op-amps, and I'm hoping that we will wrap it up at this point by the end of today, and then next week start talking about transistors. And of course, we will always come back to things. So, but I think for this level, it's fine. So, all right. So op-amps. What I'd like to do is to do a few more examples, but examples that are kind of maybe known as some specific applications also, and discuss some important issues. And I would like to, and by the way, if you couldn't make it to the tutorial yesterday, please make sure you go through the lecture notes there. And I will soon post the video as well, because that's also really very much part of this discussion. Okay. Anyway, so now I would like to start with a question that I asked you guys about last time and ask you to think about it on your own. So let's see if we can gain some insight by looking into it. Let's consider this circuit. The simple inverting amplifier. We solved this last time, assuming an ideal op-amp. And remember that for an ideal op-amp, the gain, the open loop gain of the op-amp was infinity. The input resistance was infinity, and the output resistance was 0. That means that the two input terminals of the op-amp do not take in any current. The output terminal can provide any current. And the voltage difference between the two inputs is multiplied by infinity to give you the output voltage. Now, if you've built a circuit in such a way that the output is not infinity, or in practice, it's not saturated to one of the supply voltages, then it means there should be no voltage difference at the input. Because a finite V out divided by infinity should give you 0. Would give you 0 as the voltage difference between the two inputs. And this is the kind of really helpful knowledge that we use to solve circuits like this. For instance, we said here we could solve it very easily by saying if this node is connected to 0 volts, your ground, well, so is this one, because the two input nodes should have 0 voltage difference, and therefore there is this current, which is simply VI over R, which then continues here, because there's also zero current going here, as well as here. And then the voltage difference at the output would simply be 0 that you have here minus the drop on this RF. So V out would simply be 0 minus RF times that current, which is VI over R. And this is how we concluded that we had a gain, an inverting gain, because it's a negative sign, proportional to the ratio of these two resistances, assuming an ideal op-amp. Now I'll draw another circuit for you. And I ask you what the gain is for this circuit. Well, I guess this is the question I asked you to think about. Let's do a clicker question. Next question. If you answered A, then do you think there is a difference between the two? It's simply yes or no. Well, if I wanted to calculate the gain, what would I do? I'll start saying 0 volt here. So that would translate to 0 volt there, would give me VI over R. And then 0 current here as before. So this is going like that. I would get V out again equal to minus RF over R V in. Correct? Have I missed anything here? Does anyone want to raise any objection? So let's see what the assumptions are that I'm using. I'm assuming that this is an ideal op-amp, 0 input current. That should be fine. I'm assuming that the output can tolerate any current, so this current can flow back. That's not a problem. I'm assuming infinite gain, and since V out is going to be a finite value, then that divided by infinite gain should give me 0 difference at the input, which is why I have transferred this 0 volts from the lower to the upper input. And then everything else follows from that. Would anyone like to challenge any of those assumptions? And it is an ideal op-amp. Well, let me ask you the question in another way. So of those assumptions that, let me repeat the assumption. I said we have infinite input resistance. That's a feature of the op-amp, ideal op-amp, right? 0 current going in. And any current at the output, again, ideal op-amp, no problem. The ideal op-amp also has a gain of infinity, open loop gain of infinity. That's also its feature. I'm not questioning that. But I used that to conclude that the two inputs are at the same voltage, right? How did I use that? Again, remember, this is what I'm saying. I'm saying if the two inputs, you call them V1 and V2, sorry, the output is A times the difference on the input. Now, granted, this is infinity. But this does not necessarily mean that the inputs are at the same voltage. It means either they are at the same voltage or the output is infinity. Now, the output is infinity means it gets stuck to one of the power supplies, means saturation. It goes beyond the linear region of the characteristics. Okay? At which point, this equation then breaks down because the output just becomes a constant value. So remember, this equation was valid only in the linear region. and not in saturation. In saturation, you can give it a voltage difference at the input. The output won't change. It's stuck near either the positive or negative power supply of the op-amp. And that's what we saw last time. So the assumption that perhaps I should question, not just in this circuit, but in any circuit, is whether the op-amp is operating in the linear region. And this is something that in the examples we've seen so far, I've kind of kept saying, assume that the op-amp, assume that the circuit is built such that the op-amp is within its linear region. Okay? But why should you accept that assumption? What I'd like to think about a little bit here is what makes it stay in that linear region. Let's think a little bit about the first circuit. Assume I built this in the lab, the circuit. I built it in the lab. And so I assume that the op-amp has these voltage supplies. So let's say it's connected to, it's powered up by plus 15 volts and minus 15 volts. And the ratio of these resistances, assume, is 10. So this is 1 kilo ohm, and this is 10 kilo ohm. And I give it an input VI of 1 volt above ground. What will the output be? It will be minus 10 times 1, right? Minus 10 volt, right? And it's within the linear region. It has not reached the voltage supply on either side. The op-amp is not saturated. Things are happy. And this is sitting like that in the lab. Now imagine there is a burst of noise somewhere, electromagnetic noise, that comes in and momentarily increases. There's a little bit of noise that falls all of a sudden on the negative input that increases this, the value at the negative input. Okay? So right now it's 0 volts, right, at the negative input. Assume that there is a little bit of a noise, and momentarily that there's some signal induced there raises it to 10 millivolts. So momentarily, the negative side becomes more positive than the positive side, right? You have 10 millivolts. If the negative input of the op-amp becomes more positive than the positive input, what happens to its output? What does the op-amp want to do at the output? Wants to drive down the output, right? Look at this equation. V out is that. Right now, let's say both of these were 0. But if I momentarily increase V1 by a small amount due to some noise, then V out wants to become a lot smaller, right? So V out in the circuit will go down due to the response of the op-amp. What will that do for the voltage right here at the negative input? What consequence will it have for this if that V out goes down further? Look at these two resistors. Between Vi and V out, essentially you have a voltage division to get the voltage of the highlighted node. If I drag down V out, the voltage of the negative node, the highlighted node, will actually just go down because of the way the resistors are connected. So that there is an effect that counters the noise that had momentarily raised this voltage. So it stabilizes the circuit. Now imagine the opposite happens. Imagine momentarily that you have a negative noise that draws down the voltage of the highlighted node momentarily. Then V1 goes down, the op-amp wants to increase Vout. An increase in Vout through this path of voltage division between these two resistors will lead to an increase in the voltage of the highlighted node, and again will stabilize things to back where they were. Now what happens in this circuit if I have the same noise issue? If I have momentarily, if things are sitting like this and they're happy, and assume that things are like this, but if momentarily I happen to have a small noise that for a split second raises the voltage by a small amount on this positive node, what will happen to the output of the op-amp? If the voltage on the positive node increases momentarily, the output increases. Now that increase in the output, again through this resistive connection, is fed back to the input. And reinforces the increase at the input. But then through the op-amp itself, the output will go further up, which then will further reinforce the increase at the input. And so on, and so on. And before you know it, the op-amp output is stuck at saturation. And if you happen to have a small negative noise induced on this at some point, the op-amp will go the other way. So this is the notion of feedback, negative feedback versus positive feedback. The first circuit has a negative feedback. What happens through this path, if you have a small change at the input due to whatever you have, even noise, that change going to the output will be fed back in a way that, or the output will change in a way that when translated back to the input, it will oppose that instability, that change. That's called negative feedback. In this case, on the other hand, if there is a change in the input, the change in the output will be such that it will reinforce that change at the input, and it will drive things toward instability. And this is called positive feedback. So the answer is you have to be very careful. Yes, this gain can be the same if you're doing this on paper, and if there is no disturbance and everything are ideal, and you have set the circuit from the beginning in that mode at those values, and you're not touching it, then yes, you will get the same. But as soon as there is any change in the lower circuit, it will get stuck at saturation one way or the other. Whereas the upper circuit won't. It will work the way you want. So the answer is the first circuit has negative feedback, and remains in the point, in the condition that we solved. It's in a stable condition. So this is negative feedback. The second circuit has positive feedback. and will leave the condition that we showed. With the slightest disturbance. And go towards saturation. So it's unstable. Here's a mechanical analogy. Consider this. If I have a surface like this and I place a marble down here, it will stay, right? What if I flip the surface the other way around? Well, if I place it at the very top, it will stay. And if there is no breeze, no disturbance, everything is ideal. But as soon as there is any disturbance, any shaking, it will roll down the hill, right? The difference between a stable and an unstable condition. So now I'm not saying, by the way, that this positive feedback is necessarily a bad thing. It depends on the application. There are great things that you can do with positive feedback. But if you're trying to make a non-inverting, an inverting amplifier like we've shown, the top one will work, the bottom one will not work, because you will always have some disturbance that will push this out of its equilibrium condition. Okay, so this is not a good circuit. Now, the notion of feedback is a very fundamental and broad concept, and again, something that you would first, or you would at some point study from a system level point of view, for instance, in control. In electronics, it's very, very common and ubiquitous. And here, we are not discussing feedback from a theoretical point of view. But I'm hoping that this gives you a feel for what can actually happen. And the reason why we connect our feedback path to the negative and not the positive side of the op-amp. This also reminds us that when we get a circuit, we have to, in general, there's no guarantee that it's been built properly. We have to consider whether there is proper feedback to make it stable. Okay. Now, by the way, I'm not saying that the top circuit will never reach saturation. Of course, if you increase the input voltage, if you give it an input voltage of 2 volts, it wants to come up with a minus 20 volts at the output. That's beyond the linear range, and it will get stuck at minus 15. That's a different matter. That's not because of the feedback issue. That's just because you have increased the input so much that the output has gone out of range. And of course, you should always consider that possibility as well in any circuit. Okay? So subtle but very important issue. Again, I ask that you go home and try to do this thought experiment of each of these circuits. If you make a small change to one of the inputs, either increase or decrease, see how that would affect the output through the op-amp, and then how that would affect the input again through the feedback path, and see whether it leads to a stable or unstable condition. Okay, so this is one of the key things I wanted to discuss. Yeah. Yeah, so you might be saying maybe I'm doing something a little circular. You see, ultimately, when you're trying to analyze a problem, a physical system, you have to find a solution that works. And some systems, by the way, might have multiple solutions that works, right? Multiple stable configurations. Here, the way I approached it was this. I was saying, well, you know, if I have built this circuit such that it does stay in the linear region, and I know that equation holds, and V out is a finite value and it's not saturated, then I would naturally conclude that the two inputs have to have no difference in voltage, right, from that equation. This is an assumption, if I assume V out to be a finite value and not saturated. Right? That is dictated by the opamp. Absolutely. So in reality, that difference will be a very small, a very, very small number, and multiplied by A, V out will be still something within the range. So the difference being 0 is an approximation for a very, very small number. Okay? But the point is that once you find this solution, you will see that V out is well defined, is not defined by the op-amp itself, is not defined as 0 times infinity, is defined as by what the resistors dictate in the circuit, right? So it's not ill-defined. It's well-defined by the rest of the circuit. That's the key. With this out of the way, and I know it takes time to get used to this concept. Again, maybe this course is a little bit unusual in that it tries to really do some electronics in a short period of time without you guys having seen all the other theory that underpins some of these things. But I hope at least qualitatively we can get a feel for this. So now I want to run through a few other example applications. Let's solve this circuit. Do this on your own. Ideal op-amp. Find V out as a function of the 3 input voltages, V1, V2, and V3. Okay, maybe time to take a look together. Now, again, assuming that I am not in saturation, and this is a proper negative feedback circuit, and the inputs are not driven beyond limits that would lead to saturation. And these are all things to be verified and kept in mind, of course. But assuming all of that, the solution is very similar to what we just saw. You have 0 volts here. That will lead to, and again, notice the order of things I'm doing. Especially if you've had some difficulty so far, take a look at the board. In terms of the order of things that I'm doing, that's the logic there. I know that this is, the positive side is grounded. That's 0. It's because of the circuit that I end up, because of the op-amp and the negative feedback configuration, that I will end up with 0 volts here also. That becomes a virtual ground. It's not physically connected there, but it has the same voltage. And then that will make it very easy for me to know all these 3 currents. This becomes V1 over R1. This becomes V2 over R2, because on the other side I have 0, and this becomes V3 over R3. And these add up in this branch. Sorry. They add up and continue going that way, because there is 0 amp going in to the op-amp. So by KCL, they will just go there. And so the output voltage simply becomes this. 0 volt, which is this node here, 0, minus RF times the sum of those 3 currents. So maybe you can think about it more like this. V out is with a negative sign, this. This is a summing amplifier. It's something that does the sum of 3 different voltages, each with an amplification factor determined by these ratios. And it also has a negative sign, but that's fine. If you don't like the negative sign, you can put an inverter after it. You can put an inverting amplifier with a gain of 1 afterward, and you'll get rid of that minus sign. But this is adding voltages with ratios. So this is a well-known application. This is called a summing amplifier. An adder. And it doesn't have to be limited to 3 inputs. You can have 20. Yes. Oh, you can also make non-inverting amplifiers. We also saw a non-inverting amplifier last time. Okay? So here's a question for you guys to think about as a small side problem. Can I use the non-inverting amplifier configuration to do summation of multiple voltages so that I don't have the negative sign? By the way, can I use this as a digital to analog converter? So that would be a device, a circuit that takes a digital input. So let's say you have 3 bits, zeros and ones, in a circuit maybe represented by 0 volts and 5 volts for 0 and 1, and then converts it to an analog signal. Yeah, exactly. So you're saying have the proper ratios here so that they give you the proper weight factors between your various bits or digits based on their significance, right? So you have your least significant bit and most significant bit. And if you have a byte with a number of zeros and ones, each will have, the first byte, the first bit on the right-hand side will be just 0 or 1. The next one and the next one and the next one will progressively represent higher powers, right? So have these ratios of resistances correspond to those powers. And then when you add these, and if your inputs are those digital signals, 0 or 1, your output will be an analog that corresponds to that digital signal. Consider the usage of a circuit like this for digital to analog conversion. Let's look at another circuit. And something that maybe I'll ask you guys to think about a little bit before I draw it. We just saw an amplifier that does a weighted sum, right? This is a weighted summing amplifier because it adds things with different weights. How about a difference amplifier? Can you think about designing using a single op-amp, not a big circuit, a single op-amp, a difference amplifier, so that it takes 2 inputs and it gives you the difference of those 2 at the output with some weight factors again, based on the things that we've seen so far? Does anyone have any suggestion? Here's one way to think about it. If you want the difference between two things, you want one of them to appear with a positive sign, the other one to appear with a negative sign, right? Now, so far, we've seen two amplifier configurations, inverting and non-inverting. One of them had a positive gain. The other one had a negative gain. See if you can somehow combine these into one circuit using a single op amp. Take a look at this. This was my simple inverting amplifier if I grounded the other side. But let me not ground the other side. Let me do this. Now, if I call this V1 and V2, and this RF and R1 and R2, let's call this R3. So now solve this problem. What is V out? All right, let's take a look. Again, I will first note that I do have a negative feedback, and I'll start by assuming that this, and by the way, the op amp is ideal. I'll start by assuming that it's in its linear region of operation, and of course, I will always have to keep in mind during actual operation that I don't go beyond that limit in terms of the value of the output. And so that puts some boundaries on what the inputs can be. But assuming that we are in that desirable mode, let's see what we can tell about the circuit. Well, first of all, the op amp is ideal. So again, we have 0 amp going in here and 0 amp going in there. This node voltage, let's call it V3. What is capital V3? Well, the current going through R2 will go also through R3. These two are effectively in series. And you have a simple voltage division there. So V3, the node voltage there, is R3 by R2 plus R3 times your input voltage V2. Now, if things are doing their job, then you will end up getting the same V3 on this node. It will be transferred there because of the circuit, the op amp wanting to keep the two inputs at 0 difference in voltage. And if you have V3 there, then you know this current. This is going to be, let's call this little I. I is going to be V1 minus V3 divided by R1. And by KCL, the same current is going to go all the way through RF. So V out is going to be V3 minus RF I. And so that's V3 minus RF over R1 V1 plus RF over R1, R1 V3, right? Which I'll then simplify as 1 plus RF over R1 V3 minus RF over R1 V1. And if I replace V3 from there in terms of V2, which is my input voltage, I'll have R3 over R2 plus R3 times this. Sorry. So this is your V out. So it's some weight factor multiplying V2 minus some other weight factor multiplying V1. Now, please verify that I did the algebra correctly. Okay, to be double checked by you. It's a good exercise to solve it on your own. And of course, the values of R1, R2, R3, and RF are your design parameters. So you can choose them maybe somehow such that the two weight factors are equal, if that's what you desire. Okay. Now, what if I had connected V2 directly to the positive? So if I did not have R2 and R3, and that's basically what you were suggesting, right? V2 with a factor of 1 connected to the positive here. How would my solution change? Well, if I had V2 directly on the positive, this node voltage instead of some new value V3 would be just V2, which would appear up there. So my solution here would change to V out being V2 minus RFI. Now, if you add things up, what will you get? You will get the equivalent of R2 being 0. Go see if that works out. Notice all these things that I'm doing now are not, they are just solving a circuit. The only piece of information that you know that's new here is that there's this device that doesn't take input current and would like to make sure the two inputs are at the same voltage because of the circuit. But the rest of the solution is just your basic circuit solution. So I really ask you guys to go through these and not view these as things that you have, patterns that you have to memorize. Patterns, of course, that you have to recognize over time through practice, but you should really be able to go through the derivation. So double check to see if it works out the way I just explained. This is a good time to take a break. Now, I have a question here for you guys. I have solved this circuit without having connected anything to the output, right? Now, maybe I was just interested in that output voltage. Maybe I was just going to connect a voltmeter there. And a voltmeter does not draw any current, so an ideal voltmeter. So it's as if it's not there. No problem. It's like this. But what if I wanted to use this output to actually drive a load, to give a current to a resistor? So what if I had something like this? What if I connected a resistor here? How would the answer change? Let me ask it in another way. Which one of the things that I did in blue would change because of the inclusion of this new resistor? None of these steps would change, right? So I would get the same V out. That's very nice. Now, what does that say for, now, did anything change in the op-amp at all? Is there any change in the circuit? I just suggested that V out is not going to change, but is there anything else in the circuit that did change? There will be current. You see, before this current, if I didn't have that extra resistor, this current would have gone all the way like this, had to go back to the op-amp. Now that current will have to split. So instead of going like that, it will have to go here. Part of it has to go to this resistor. And the rest will go to the op-amp. So the output current of the op-amp has now changed to accommodate for what we need to provide here. Now, this current up here is fixed. The current I going there is fixed. So depending on the value of this resistor, which will determine the current there, imagine if we call this RO, this will be V out over RO. Depending on how much this current is, the output of the op-amp will have to adjust itself. The output current of the op-amp will have to adjust itself. And of course, if you have an ideal op-amp, which can give you any current, then no problem, right? In reality, though, obviously you have to take into account when you actually design a circuit to build in the lab, you have to do these calculations and see that the current that you are going to send to the op-amp or pull out of it is going to be within the range that the data sheet specifies. So in this case, an ideal op-amp, in this problem, the inclusion of a load resistor did not change the output voltage, although it did change the output current of the op-amp in order to accommodate for that new current that has been added in the circuit. So this is one thing I wanted to point out, and you would see this in many circuits where you are actually trying to use the op-amp to drive something. Now I'd like to build up on this circuit and use it for something. So imagine you're trying to use this to sense some very small voltage difference somewhere. It's, pick up a sensitive signal somewhere, a small voltage difference. And that's a very typical scenario, right? In fact, in a huge number of problems, that's what you're doing. You have a small signal somewhere you're trying to amplify or measure a difference between 2 points. Is this a good circuit? Can I just, whatever 2 points I have, can I just connect them to V1 and V2 and use the circuit to get the difference with some amplification factor? Or is there something to be concerned about? There is something to be concerned about. It might be hard to tell from the circuit itself. But when I connect this point V1 to something, right, one of my inputs, well, where does this current I come from? The current I that I have drawn here. Or for V2, this other current here, where does that come from? Well, it comes from whatever this was connected to, right? What if that circuit, that point, whatever element it was, an antenna or what have you, what if it cannot provide these currents? What will happen then? Imagine this current I, if you calculate it, you put some numbers here and you get I equal 1 amp. And V1 is a small battery that can only give you 10 milliamps. Then what happens? Let's see where things start going wrong. So you have a circuit here that if you do give it, let's say, 1.5 volts here at the input V1, let's say it requires 1 amp for this to function, if this current I in blue is 1 amp. Well, it means that whatever is connected here will have to provide that. And if it can't, then these equations break down, right? So indeed, you will not get the output that you're expecting, and something somewhere will go wrong. How would you prevent this from happening? This is essentially the same question as saying, if I have a voltage source, a small battery, and I say connect it to a resistor. So I take you to the lab and I give you a small battery, and I give you a resistor and I cover it. I say, you don't know the value of this resistor. Connect it across this battery. Will you do it? Will you do it? I wouldn't do it. Good. Because what if that resistor is 1 ohm and the battery is 10 volts? So that requires 10 amps, and the battery can supply only maybe half an amp, or what, right? What will that do to the battery? It will drive it way above its current limit, probably heat it up, at the very least damage it, drain it, right? Or worse things could happen. So you don't do that. Same here. So depending on what this circuit requires to function, you cannot connect it directly to whatever you want, because that thing is going to have to provide these input currents. It's a matter of the input resistance of this circuit. It's not the input resistance of the op-amp anymore. We are looking at the points V1 and V2. It's the input resistances that are being seen at those points. Okay? So if you wanted to make a safer circuit to have to avoid this issue so that you can connect a wide variety of input sources to it without having to worry about whether things go wrong like this, could you add something to this? I'll still draw my difference amplifier. I just don't want to connect these points directly to whatever inputs I have, because maybe the inputs cannot provide the current that this needs. Maybe the input resistance here is not high enough. What should I add before these? Something that we saw last time. The question is, if I want to connect some V1 and V2 here, I have to make sure that whatever that circuit is that gives me the V1 and V2 can provide these currents, the blue and the green currents, right? What if they can't? So I want to build something safer that does not impose these input currents to whatever else I'm going to be connecting to it. That is not going to load whatever else I'm going to connect to it. Something I drew last time. How about this? I added 2 voltage followers or buffers at the input. Now, what is the current that you need here? What is that blue current? This current here is 0 amp, right? That's the input current of an op-amp. For an ideal op-amp, it would be 0 amp. And this current here would also be 0 amp. So the voltage followers here have provided an isolation, a degree of separation between whatever you are going to connect at the input and whatever was required here, which was something. And here, something else. Those are now provided by these input stage op-amps. This is the simple version of what you would call an instrumentation amplifier. A simple version of an instrumentation amplifier. The 2 voltage followers at the input provide a degree of isolation. Now the input resistance that input V1 sees is infinity. There is no current being drawn. Same for V2. And any necessary current in the subsequent stage will be provided by the first 2 op-amps. You have your V out here. Now, by the way, you might say, now that I have paid the price of 2 additional op-amps, I might as well use them to also get some gain. Why use a voltage follower? Maybe I can also include some resistor somehow to get some gain from the first op-amps also. So let me also write that down. Yes, yes, exactly. So the question is, will the op-amp provide anything that the circuit needs? And the answer is, again, assuming an ideal op-amp, or for a real op-amp, assuming that you don't ask to go beyond this range, then yes. Like in this example here, if I did not have a resistor here, well, the entire, that current blue, the blue current I would go to the output of the op-amp, and the op-amp would accommodate it. If I have this, now a part of that current will have to go here, and the op-amp will accommodate the difference. And depending on how much this current is, the op-amp might have to either sink the current or source some additional current. But for an ideal op-amp, no problem. A real op-amp, as long as it's within the range that it can supply. Yes, we were just reminded that we are not gaining energy for free, and that's absolutely true. And I hope I did not imply that we have created a free energy machine here. We absolutely have not. What you've done here is that, so these input op-amps, of course, you have to connect to their power supplies, and these currents are ultimately coming from those power supplies. What you have done is you have isolated V1 and V2, which is something that maybe comes from the antenna of your phone. And it might be an extremely faint signal because you are very far from the base station. And a tiny signal on your phone's antenna will be able to provide only so much current, right? So you say, OK, fine. I won't bother you for additional current. You just tell me what that voltage is, like what I have here. Any current that I need to drive my amplifier, my difference amplifier, I'll pull through my phone's battery, right? That's an example. This is absolutely not about free energy in any way. Nowhere in this class, the whole term, if at any point you thought I implied free energy, there was a misunderstanding. We did not violate conservation of energy. Again, there are standard designs with, you can progressively make it more sophisticated, but this is the basic idea. And like I said, you can now change the input stages from a simple buffer or a simple voltage follower to something that will give you some additional gain. One other thing I wanted to emphasize here, and we've talked about this before, but just again emphasize the modularity of a lot of these circuits that we are talking about, right? So a voltage follower, we could just now take it as a module, put it in front of a difference amplifier. So we are cascading op-amps. And the reason for that is, as you saw, the output of the first op-amp could essentially accommodate anything that was needed in the input of the second op-amp. It was because the output of the first op-amp could provide any current, because it had zero output resistance. And so this concept of stacking op-amp circuits like that, having something with some gain and then multiply. You can even stack 3 stages of gain. Imagine you want a gain of 1 billion. Okay? If you wanted to do it with a simple inverting amplifier, if you wanted a gain of 1 billion, your ratio of RF over R has to be 1 billion, right? So you need a 1 ohm resistor and a giga-ohm resistor. Okay? Something about it doesn't sound right. But what if you said, instead, I will make an amplifier with a gain of 1,000? Now, maybe a lot more reasonable. I'll have a 10 ohm resistor and a 10 kilo ohm resistor. Give me a gain of 1,000. But then I'll stack 3 of these one after the other. Right? Now I get my gain. So this concept of stacking or cascading op-amp circuit modules to gain new functionalities or improve is very common. So, and this is an example. Cascading op-amp circuits. We saw another example yesterday in the tutorial. But again, you should always understand the full circuit to make sure that these different modules are compatible with each other, right? Obviously. I'd like to show one other example and then point out a few quick things, and we'll have to wrap up then. But here's another example. So we saw some cases, some circuits that involved, for instance, capacitors, or an example yesterday that involved an inductor. So I want to draw another circuit that has a capacitor, and let's try to figure out what this circuit does. Can you guys take a few moments and think about what this might be doing? And let's assume that the supplies are connected to plus 15 volts and minus 15 volts. And assume that at time t equals 0, this capacitor is uncharged. Maybe even assume that these are just R. All of them are R. And this is C. Let's assume that the capacitor C has 0 charge, and we are at time t equals 0. Now, maybe everything is sitting comfortably with having 0 volt at either one of the inputs and 0 volt at the output, and there is no current going through any of the resistors, and everything is happy. But if there is the slightest disturbance, so let's imagine that all of a sudden you have a tiny noise that finds its way on the positive input. So I'm going back to the same positive feedback example that we saw earlier, because you see clearly here that we have made that positive feedback connection. So if I have a very small signal that finds its way here, and so this voltage goes up a little bit. So assume that this was 0 volts because the capacitor was uncharged. And somehow there's a tiny noise that raises this point a little bit. What does that do to the output of the op-amp? Well, now you have a positive voltage difference between the two inputs times infinity. It will give you infinite voltage at the output. But of course, it won't go to infinity. It will saturate. So the output will immediately go up to 15 volts. It will saturate at that 15 volts. Now look at this circuit. If I have 15 volts here and 0 volts here, what happens in this path? I just have an RC circuit. I have applied 15 volts here, there's 0 volts on that side, so there's a current going through the resistor R, and that current will charge the capacitor, right? And by the way, if the output was 15 volts, what was the positive input? If the output gets stuck at 15 volts, the positive input will get stuck at 7.5 volts, right? I have a simple voltage division between the two resistors. Because remember, there's no current flowing into the op-amp. OK, so you have 7.5 volts on the positive side, and the RC circuit at the top starts charging the capacitor. If you give it infinite time, what will the ultimate voltage of the capacitor be in that RC circuit? Forget about the rest of the circuit. If you just had the top portion, you have an R and C, you applied 15 volts across the series combination of R and C. What will eventually end up being for the capacitor? 15 volts, right? It will, at some point, be charged up to 15 volts, and the current will stop, right? But now remember the full circuit. As the capacitor voltage is increasing, at some point it reaches 7.5 volts, right? And then it will go slightly above. It wants to continue going. What happens when it reaches 7.50000001? What will the op-amp do then? The op-amp will flip, because now the negative side has become more has a higher value than the positive side. So the op-amp will now take that negative input and multiply it by infinity, and wants to go to minus infinity, which really means wants to go down to minus 15. Well, wants to go to minus infinity, but will get stuck at minus 15 volts. Now the capacitor has just barely surpassed 7.5 volts, but before you let it go all the way to 15, you have changed the output to minus 15. What will the capacitor start doing now? It will start discharging. How far will it discharge? By the way, when the output switched to minus 15 volts, what happens to the positive input? Will drop to minus 7.5 volts, right? So now the top input is at 7.5 volts. The bottom input is at minus 7.5 volts, and the output is stuck at negative power supply. Now the capacitor will discharge. And it will discharge until the top pin, the top input, reaches minus 7.5 volts. And as soon as it goes ever so slightly below minus 7.5 volts, what will happen to the output? It will switch again. So the output will go back and forth in time. And the capacitor keeps charging and discharging. So this is an oscillator. Maybe a clock for your computer. So this is another example. What I would like to point out is that, of course, so far we've looked at examples with ideal op-amps. Like other elements, they are not ideal. There's a few things to keep in mind. First of all, the gain is not infinity, but it is a very large number. So the qualitative behavior of these circuits that we've discussed doesn't change. The numbers, of course, will change. To get a feel for that, I will give you a small problem to work on at home. Solve a voltage follower assuming the open loop gain of the op-amp to be A, not infinity. Derive an expression for V out over V in. And you should see that the effect of that finite value of A. And in the limit, set that A to infinity and see if you recover what we have done already. That's just to give you a feel for what this would do. Here's another point I'd like to draw your attention to. And that's the fact that, we've said the input current is 0 for an ideal op-amp. Well, a real op-amp, the input current is not 0. And there is this thing called the input offset current. And so there, you can imagine as there being a current going through each of the two inputs. And for instance, the difference of those is called the offset current. But what that does in practice is that if you build a circuit without being aware of that input offset and adjusting it somehow, making up for it to eliminate its effect, very likely your circuit will not work in the linear region. Because things are normally so sensitive in an op-amp circuit that a small offset at the input that you didn't expect could get amplified and saturate your output. That's one thing. There's also this thing called the input voltage offset. And that means, let's say if you build an op-amp circuit and you assume that an input voltage of 0 will produce an output voltage of 0. But again, in practice, you build it and it doesn't. And these are because of the non-idealities of the op-amp circuit. So when you buy an op-amp, and you will see this in your lab, there will be some extra pins that normally allow you to compensate for some of these. Okay? So this, to get into the details of this would take a lot of time. And as far as this level of discussion is concerned, it won't really give us all that much more insight. But I think on a practical level, it's important for you guys to be aware of this. And so what I ask is that when you do your lab next week, which I'll post soon, where you have an op-amp, take a close look at the pin configuration of the op-amp and identify pins that are there for adjusting things. Okay? So I'll just make a note here. In practice, be aware of the issues of offset voltage and input current. Again, this is not something that I expect you guys to know a whole lot about, because we don't have time to get into it. But it's something I wanted to you to be exposed to and look for in your op-amp data sheet. Okay? Thank you.